Can everyone hear me at the back?
Yep.
Yeah. Brilliant. All right. So I'm going to talk about supermassive black holes, and I'm going to talk specifically about the supermassive black holes that are really elusive to find. They're really tricky to find. They're hidden. And these are the kinds of objects that I've spent a lot of my career trying to track down. So let's start with the basics. So what is a supermassive black hole? Well, to understand that, we first need to understand what a black hole is. So a black hole is basically a region of space-time that is so dense that nothing, not even light, can escape from it. And supermassive black holes, as the name sort of implies, are really the monster black holes, the biggest black holes in the universe. So these are things that weigh anywhere from several million to several billion times what our sun weighs. So that's how we define a supermassive black hole. And the reason that supermassive black holes are interesting is because we now know that there is a supermassive black hole sitting at the centers of pretty much all galaxies that we see in the universe. So when we look out and take pictures of the sky with our big telescopes, we see all sorts of different galaxies. They come in all sorts of shapes and sizes and colors. And we now believe that there is a supermassive black hole sitting at the center of all of these galaxies. So in this way, these supermassive black holes are pretty common. But in some other ways, as I'll get to later on in the talk, they're actually pretty rare, pretty exotic phenomena. Now, when I've placed these supermassive black holes here at the centers of all of these galaxies, I've actually grossly exaggerated the scale of these supermassive black holes relative to the size of the galaxies. So in reality, if we were to take a galaxy like this and we were to put the supermassive black hole at the center, then in this kind of scale, you really wouldn't be able to see it in the picture. So even though these supermassive black holes are very, very heavy, so as I said, few million to few billion times heavier than the sun, nevertheless, the actual region that's occupied by these supermassive black holes is very, very small. So it's like the equivalent of placing a single grain of sand at the center of the Earth. So that's the size, that's the kind of sphere of influence of these supermassive black holes. Right, so I already said that there's these supermassive black holes we think sit at the centers of pretty much all galaxies. And one of the reasons why astronomers, myself included, are really interested in studying these supermassive black holes is because about 20 years ago or so, there was this amazing discovery made that when you looked at the supermassive black holes and you weighed them, so looked at how massive they were, there was this correlation with how massive the galaxies were in which these supermassive black holes were sitting. Now this is kind of surprising because, as I said, these supermassive black holes are occupying this very tiny region, like a single grain of sand at the center of the Earth. So this is like saying if you took a whole bunch of planets like our Earth and you put grains of sand in them, somehow the bigger the planet, the bigger the grain of sand. And that kind of doesn't really make sense given when you think about the scale. So we need to find some way of explaining this, and we still don't really fully understand why the universe is like this, why the bigger black holes sit in the bigger galaxies and the smaller black holes sit in smaller galaxies. And that's one of the main things that I've been trying to do in my research, is trying to work out how these supermassive black holes actually influence the properties of their host galaxies, or vice versa. Right, so supermassive black holes, as I said, they're pretty common in that they sit at the centers of pretty much all galaxies. However, as I said at the beginning, these black holes are defined to be regions of space-time that are so dense that not even light can escape from them. So that's a problem if you're an observational astronomer like me and you want to actually see something. So how do we infer that these supermassive black holes are there? Well, the way we do that is we actually observe these supermassive black holes during what we call feeding phases. So when they're actually rapidly swallowing up all the material around them, gas, dust, stars, basically anything that falls within the vicinity of the black hole. And when they're growing, when they're rapidly feeding on all of this material, what happens is the material around the black hole, just before it's going to be swallowed up, gets heated to very, very high temperatures. It emits a huge amount of energy. And so during these feeding phases, we observe these supermassive black holes as what are called quasars. And these quasars are some of the brightest lights in our universe. So they emit an enormous amount of radiation, and so you can see them out to really vast cosmic distances. So these feeding phases are relatively rare, and so these are kind of giving you that observational insight into what's going on with these supermassive black holes. And so to be able to find these kinds of quasars, these supermassive black holes during these feeding phases, we have to take our telescopes and we have to scan very large areas in the sky and sift through many hundreds of millions, now getting to billions of objects to be able to find these kinds of things. This is an object called 3C273. It's actually one of these quasars, so it's a supermassive black hole that is rapidly feeding. And what you're seeing here is actually the emission from the galaxy in which this supermassive black hole is sitting has been completely dwarfed by the material around the black hole itself. So that's what's shining really, really brightly, and that's what we're observing. So this particular quasar, 3C273, is basically generating the equivalent of 2 trillion suns of power. So, or in other words, if you take this nuclear power plant, which is one of the largest power plants in the US, the amount of power being generated by this feeding supermassive black hole is basically 1 trillion times 1 trillion times 1 million times the amount of power being generated by this nuclear power plant. So it's a lot of power. These are some of the most energetic objects in the universe. So this particular quasar 3C273, it's about 2.5 billion light years away. But if we were to take this quasar and we were to put this in our own galaxy, this would be the brightest thing in the sky, so it would be brighter than our own sun. So that again gives you an idea about how bright these quasars are and why we can see them out to such vast distances. Okay, so to be able to find these supermassive black holes, we look for them during these growing phases, and we look for them with big telescopes. This telescope, I would say, has been the most prolific black hole hunter to date. This is a telescope called the Sloan Digital Sky Survey Telescope. It operates at visible wavelengths, so here's the electromagnetic spectrum. This is a whole range of different frequencies of radiation that we observe. Most of the feeding black holes that we've discovered have been discovered using observations of visible wavelengths, although when these black holes are feeding, they actually emit radiation across this full spectrum. So using this telescope, we now know of more than 500,000 of these feeding supermassive black holes going out all the way into the very, very early universe. Right, so let's do a quick recap. So I've told you that supermassive black holes are black holes that are weighing several million to billion times the mass of our sun. They live at the centers of most galaxies. We've seen this correlation between the supermassive black hole and the galaxy in which it's sitting. The bigger supermassive black holes sit in bigger galaxies. We observe them when they're feeding, and during that time they shine brightly as quasars. And using the Sloan Digital Sky Survey Telescope, we've now managed to find hundreds of thousands of these feeding supermassive black holes. Okay, so let's come back to this connection now. And we want to understand why it is that these bigger black holes are sitting in bigger galaxies. So to understand that, let's first understand how galaxies grow. So how do galaxies get big? And the easiest way in which you can grow a galaxy is basically by crashing it into another galaxy. So you take two galaxies, you merge them, and we actually see beautiful examples of this happening in the universe. And when you do that, you might expect if each of those galaxies has a supermassive black hole at the center, then you might merge those two supermassive black holes as well. So then if those galaxies, say, were equally massive, you produce a galaxy that was twice as massive, and then the black hole would be twice as massive as well. So these galaxy merging events we observe, they're very dramatic events, and they're probably giving us some clue about how these black holes and galaxies are growing in step. But what else happens during a merger? So what happens during a merger is when these galaxies collide, that brings in huge quantities of dust, gas, stars, all the things that make up galaxies. The gas gets compressed. Out of that gas, new stars are born, so that's what's seen here. These are the famous pillars of creation, and you can see these gas clouds out of which new stars are being born. Then, as the stars evolve, the most massive stars die off as supernovae. The supernovae are actually really important because they inject all of the material that's inside the stars, all the metals, all the dust, they inject that out into the galaxy. So when these supernovae go off, they produce a huge amount of dust and other heavy elements, and they essentially pollute the galaxy. So there's a huge amount of debris that's produced as a result of these supernova events. And what the dust does is it essentially obscures our view in visible light. So it makes things a bit murky, it makes things a bit harder to see, essentially. So this is just to give you a visual example of that. Here's the Carina Nebula seen in visible light. You've got this huge kind of cloud of dust and gas, and you can't really see what's going on inside there. But now if we move from the visible wavelengths and go to the infrared, this is again the same view of the Carina Nebula, and now you can see you're able to peer through all of this debris, all of this gas and dust, and see all the new stars that are being born within this gas cloud. Very similar thing here with these pillars of creation. Again, in the visible light on the left, the view is completely obscured. You go to the infrared and you see all of these stars that you really weren't able to see with the visible light. And actually, we have examples of this kind of closer to home. So many of you will be familiar with the concept of thermal imaging, and it's the same kind of thing. So if we're looking for something in visible light and we can't see it, it might be a good idea to look for the heat being generated. So here's a person hiding behind a bush, here's the normal view, here's the thermal view, and that's exactly what we do in astronomy as well. So we move from the visible wavelengths into the infrared wavelengths, and the hope is that by tracing this kind of thermal emission, that we might be able to see these hiding supermassive black holes, things that are being obscured by all of this dust and murky material that might be generated during these merger events. And so here's a couple of galaxies that are very, very dusty, and I can tell you that both of these have feeding supermassive black holes at their center. But if you remember that picture of 3C273 that I showed you earlier, where you could just see this bright light outshining the galaxy, clearly that's not the case here. So in this case, this is a partially obscured galaxy. You can see there's something bright here at the center. That is actually the feeding supermassive black hole, but it's kind of hard to see amid all of this gas and dust. And similarly for this galaxy here. So to get around this, what we've done is actually built big infrared cameras. So most of the feeding black holes I told you were found at visible wavelengths. But now using this camera, which is the VIRCAM camera, it's mounted on a telescope called the VISTA telescope in Chile. We've actually been able to scan the sky at infrared wavelengths and try and look for these hidden supermassive black holes. So that's the camera there. There's me next to it. It really is a beast, so you can see how big the camera is. It weighs 3 tons. It has a total of 67 million pixels. And using the images of the sky that were taken with this camera, here are a couple of these kind of hidden supermassive black holes that we've discovered here in Cambridge in our group. So these little red dots here, I mean, they don't look like much, but these are feeding supermassive black holes. These are about 11 billion light years away. So the light from these black holes has taken 11 billion years to reach us. And if you were to take the Sloan Digital Sky Survey telescope, which I told you has so far been the most prolific black hole hunter, and look at these same patches of sky with the Sloan Digital Sky Survey telescope, you wouldn't see anything in these regions. So these really were new black holes that we hadn't identified before, just because we think the galaxies that they're sitting in are very murky, very dusty, maybe because they've recently had these kind of catastrophic merging events, and that's produced lots of debris, which is actually hiding the feeding activity of these supermassive black holes. Right, so that's kind of the hypothesis, is that these black holes, we didn't see them in the visible light because they were obscured by all of this dust and gas and debris. But really, as observational astronomers, what we want to do is test that hypothesis. And to be able to do that, we're now going to move further down in the electromagnetic spectrum and look at observations kind of somewhere between the microwave and radio wavelengths. And the reason we do that is because these wavelengths are what we use to trace that dust and gas. So the stuff that is obscuring the black hole potentially, and also potentially the stuff that the black hole is feeding on. So now we're not interested in in the light that's coming from around the black hole. We're interested in what's going on in the wider galaxy and seeing if there really is lots of dust and gas, and if that is what is responsible for hiding these black holes. So here's an observation, again, of one of those infrared selected hidden supermassive black holes that we found that is 11.5 billion light years away. But now we're looking at these, so you can, if I go back here, you can see in the infrared view, they just look like little blobs. You can't really see much in terms of structure, and that's because the light here really is coming from the very central region close to the black hole. But now if we take one of these and then we look at them in this kind of microwave radio emission, what we're now tracing is the emission that is coming from dust and from gas. So these are the things that make up the galaxies in which these black holes are sitting. And essentially, in this kind of color image, the bluish light is coming from the dust and the reddish light is coming from the gas. And the black hole is basically sitting over there, we know from the infrared observations, but what you can see, again, this is very, very recent data actually taken within our group here. What you can hopefully see is that there's two distinct blobs here. So we've got the black hole sitting here, but there seems to be another kind of companion galaxy right next to the galaxy. Oops. Right next to the galaxy that's hosting the black hole. And this second galaxy is located about 50,000 light years away from the quasar. So from the galaxy that's in which the quasar is sitting. And just as a comparison, our neighboring galaxy, Andromeda, is about 2.5 million light years away from us. So 50,000 light years away is really very close. And actually it's close enough that we know if we kind of calculate what the timescales are that these galaxies would merge with each other given the velocities at which they're moving, we know that this merger, this collision between the two galaxies is almost certainly happening. Some of this material that you see in between the two galaxies is almost certainly generated because the galaxies are in the process of merging. And so here we're seeing kind of smoking gun evidence that our hypothesis for why these black holes are hidden is true. So there's a merger happening, there's two galaxies that are in the process of colliding, there's lots of dust and gas being produced, which we've been able to image now by going to these microwave and radio wavelengths, and then that is almost certainly what's responsible for hiding these supermassive black holes from our view in visible light. So just in the last kind of couple of minutes, I just want to talk to you about where this field is heading, the future of this field, and again, as an observational astronomer, it's really exciting because the future really is very, very bright. So we have a whole bunch of telescopes that are coming along that are going to observe at all wavelengths that I've already discussed, so in visible light, in the infrared, and then also in this microwave and radio emission. So that's going to really allow us to put together these detailed pictures of supermassive black holes and the galaxies in which they're sitting. So I just want to talk to you a little bit about each of these different telescopes. So here is the kind of next big thing in visible astronomy. This is the Large Synoptic Survey Telescope that's going to be operational in the 2020s. It's a 3,200 megapixel camera that's going to be mounted on this telescope here, which is an 8.5 diameter mirror, so that's much bigger than any of the kind of optical visible light survey telescopes we currently have. And it's going to scan the sky over 10 years, but it's going to scan the sky really frequently. So what we're going to get is a movie of the sky, essentially. Every few days we will get images of the same patches of sky, so we will be able to build up over 10 years this movie of the sky. And one of the really exciting things about this is that these feeding episodes of supermassive black holes, they're transient phenomena. So supermassive black holes, they feed, then they turn off, they stop feeding. And so if you make a movie rather than just getting a snapshot, you're going to actually see that progression. You're actually going to see the supermassive black holes feeding and then stopping feeding. And so that's going to be really, really exciting in understanding this feeding process and what generates the light that we see as quasars. So it will detect an enormous number of objects, 37 billion stars and galaxies, and also millions of these new quasars. In the infrared, this telescope here is the James Webb Space Telescope, which is going to be the successor, essentially, to the Hubble Space Telescope. That has a 6.5 meter diameter mirror, which is actually pretty big for what you can put into space. And by going to space, you have the advantage that you're now unimpeded by the Earth's atmosphere. So it's going to allow us to get really exquisite images of the infrared sky and look for these very distant, hidden supermassive black holes that are lying behind these screens of dust. And then finally, in the kind of millimeter microwave and radio wavelengths, this array of telescopes, this is the Atacama Large Millimeter Array, is already operational, but it's kind of ramping up in capability, and it's going to continue to do so. It's eventually going to be composed of 66 12-meter diameter telescopes that essentially operate as one. So by moving these different telescopes around, you can essentially control the zoom or the resolution on the sky. So when the telescopes are really, really close together, you get a lower resolution, and when you put them really far apart, then you get a much higher resolution on the sky. And that's going to allow us to image the constituents of the galaxies where these feeding supermassive black holes are sitting. So the gas and the dust, and to put all of that together to try and build up this comprehensive picture of supermassive black holes and their host galaxies. And I'll finish there. Thank you.